All right, everyone. So now we're going to take a look at how we can use quaternions in a practical way, right? So here I have a scene, and I'm going to basically release some particles from our left-hand sphere over here. And essentially, I want to target the right-hand sphere. Okay, so I've got, sort of like some kind of cluster bomb thing or whatever. So you'll see here it shoots out 4 particles, which then explode into like a cluster, and those all essentially target the right-hand sphere. But something you'll notice here is that they kind of rotate around to target the right-hand sphere in a more natural way than just blending. If we had to do like a sort of a linear blend of the velocities, you'd get very sort of strange flipping, or some particles would turn around and face it a lot faster than they technically should, right? So we get these lovely sort of arcs, and also kind of a randomness to it, where they sort of spread out a little bit, because some of them are finding a different kind of shortest path for it to rotate around and get on track to targeting this circle, okay, this sphere. And we also have control over kind of how accurate it is, or how fast it can turn a corner, which is nice, because if we animated this right-hand sphere as well, it would do the same thing. If any particles missed, then they would go around and rotate and try. And so essentially we have like a homing missile here, okay, which is kind of cool. So we're going to achieve this using quaternions, right? Because we have these particles moving, and they're moving in a particular direction. And if we just allow sort of rotation of direction, like, essentially blending of 2 different rotations, but in a smooth way that quaternions gives us, then we can, achieve exactly what we have here. What we do not want to do, though, is do just a linear sort of lerp between the current velocity and target velocity, because then only some particles that are on like a smaller angle will look good. Others will then suddenly just rotate in a way that looks very unnatural, right? So let's dive in and have a look at what is happening here. And before we look at the actual sim, I'm going to show you just a little example of what we're doing, so that we can kind of understand the principles behind it. Okay. So I've got a sphere on the left here, and I'm scattering some points. Okay, just statically scattering points on here. And then I'm setting a velocity of these points. Okay, more than anything, I'm just essentially creating a vector that we can visualize, right? Now these points all have an outward velocity, right? So these are just sort of moving outwards in a random direction. Well, these are not random; these are moving directly outwards, but it essentially doesn't matter. Every particle has its own velocity. That's the point we're trying to sort of prove here, right? But then we have our target. So our target is another sphere over here, and this is a primitive, so it only has one single point. Okay, so it's visualized as a sphere, but really it's a point. Okay, and I'm going to use that as the target for all of these. You could have each point have its own separate target, which that could be something that you'd want to achieve, or you could have them all sort of picking a different point on the sphere, so then you'd maybe want to scatter the same number of points on the sphere, or there's a variety of ways you can do it. In this case, though, we're just going to target the sphere. So in other words, the center of the sphere is the actual target position. Okay. So what we're doing in this wrangle over here is I'm calculating my target and setting it in a variable. Okay, so we're essentially looking at the second input over here on the right. So number 1 means second input, and I'm grabbing its point position, but I'm grabbing the position of point 0. So it doesn't matter which point we're running over. We're not using at ptnum, because there is no corresponding point. We have 100 points on the left here, but only 1 on the right. So we're specifically wanting to look at point 0 on the right-hand side, so on our second incoming geometry. And that's our target. So every point here has its own velocity, but they all have the same target, which is all the way over here. Okay. And now we're going to use basically everything we've learned in all the vector maths, as well as then the quaternions, to essentially calculate a blend between our current velocity and then the velocity that would take us towards that target. Okay, so here I'm calculating an up, but actually I'm doing some randomization here. Now I will come back and explain this in a second, but for now let's just override that with this. So I'm going to reinitialize this and disable this line. So let's just give it a static up vector. Okay, I'll give it up like that, 0, 1, 0. And then later we'll come and add this, and I'll explain why just now. So here we've got 0, 1, 0, so that's our up. And then we've got our target. Now, what we have in our current speed, right? So we've got these particles that have velocity, they are moving. All we're wanting to do, and the reason we're working with quaternions here, is to change direction, not the actual speed, not the magnitude, only the direction. So let's separate out the magnitude. Before we start altering and doing anything to it, we go and store the length of our velocity in current speed. Because at the end, we're essentially going to just calculate a new direction and then multiply it by the speed, so that we don't alter the speed of our particles at all. They are, I mean, especially if these are missiles, they have their own velocity. They're actually being driven by sort of a force behind them, so they would maintain a very consistent velocity. But let's say they were knocked off path or had to change direction suddenly, and so their velocity, maybe because of drag and whatever, is reduced. Well, we don't want to alter that. You know, the rest of our sim is taking care of the actual speed of our particles. What we're trying to do is only alter the direction, right? So here's how we're going to alter the direction, and then just at the end we're going to multiply by the current speed. So this first step, we're wanting to calculate the current orientation of our particle velocities. So we take the direction, which is the velocity, but we normalize it. Okay, so we strip out the speed and we just say, what is your direction, your current direction? And then we're going to use our lookat function, which I explained to you before. So we have from, to, and up. Okay, so the from is just going to be 0, 0, 0, and that's because the direction, so the current direction, is based on our velocity, and our velocity is centered around the point. In other words, it's centered around the center of the world, not relative it's not relative to the world, as relative to the point. And so as far as the velocity is concerned, it's at the center of the world. Okay, so we use 0, 0, 0 as our from. We use the current direction of the velocity as our to, and then we give it our up. And that gives us a rotation matrix, so our current matrix. Now we're not going to use the matrix itself. We're going to do like what we explained in the quaternion lesson, where we actually calculate the orient as a quaternion. Okay. We use the quaternion function to convert our rotation matrix to a quaternion. Now this is a vector 4. So you see it's a vector 4, and it's storing 4 different values that essentially have our rotation stored in those. But as we've said before, because it's a quaternion, we can now use a spherical linear interpolation to blend, which will give us much better rotation. Okay, and it doesn't matter what direction these are all going in. There's not going to be sudden kind of flipping and popping and weird twitches and stuff. It's going to blend nice and smoothly. Now, we basically do the exact same thing, but instead of using v at v, so the current velocity, we are using the target position minus our current position, which is going to get us the difference between where we are and where we want to be, and we normalize that. So that is essentially the velocity that we would like, because if we are moving from where we are towards where we want to be, if that's the direction we're headed, then eventually we're going to get where we want to be, right? So this is what's happening here. But that is just the target direction, which we now need to convert into a quaternion. So we do the same thing. We look at this is from 0 to the target direction with the same up, and then we convert it to a quaternion. Now that we have these two different quaternions, essentially it's its current orientation and the orientation we would like it to have, we can blend using a slurp. Okay, so spherical linear interpolation, which we feed it the current orientation and the target orientation, and then a blend value. Now in this case, the blend value, I'm just giving it an actual parameter. So when I go from 0, at 0, you'll see that it hasn't changed at all because it's keeping its current orientation. And then at 1, we will get the target orientation, 100% of it, right? But as we blend, you'll see here that very smoothly they all rotate around to face where we would like them to be. So if I look at especially from the top, you'll notice it. The reason you'll notice it most from the top is because we're looking down along our up vector. So this is the vector that is attempting to maintain, and so it's going to rotate out around this. Now if we just did a lerp instead of a slurp, then we would essentially have these vectors getting squashed down. Okay. Now we're obviously afterwards we're fixing it by multiplying it by our current speed, so it has a set length. But then what you'd end up with is sudden sort of popping. Okay. So that's not what we want. We want it to rotate nice and smoothly. Okay. And so after calculating the new orientation, all we're doing is we're rotating, but we're rotating sort of like an identity vector here, like just a standard vector that is -1 along the z-axis, right? Which is sort of the standard orientation. And we're rotating that by our new orientation, which at 0, it's kind of strange because what we're doing is we're calculating the current orientation. We're blending with our target, but we're blending 0 of the target. So the target is not included at all. And then we're rotating our sort of base vector by our new orientation, which is the same as the current orientation. And so we end up with essentially nothing. But now as we rotate, or as we blend more, it then blends in the target orientation into this Q rotate. So this Q rotate is a function that is a quaternion rotate. In other words, rotate this vector by this quaternion and then return that value. So this is our new direction. And because it's all been normalized, because we literally are just talking about, a normalized vector over here. I mean, we could normalize this afterwards if you really want to. So normalize, just to be 100% certain that this is normalized. And then we multiply by our current speed, which is the speed that we had before. Okay, it's just a simple blend. So now what we're doing is essentially the same thing. Oh, hang on, sorry. There's one thing, which is, you see here how everything is rotating very nicely, as in all equally and evenly, because they all have the same up. Now that might be what you want, but when it comes to something like these missiles, maybe we want a little bit of chaos in there, a little bit of naturalness. So let's give each of them their own random normal, like random up. Okay, they're still going to blend from the current to the target. So you'll see at 1 it looks the same, and at 0 it looks the same. But the difference is in the middle. Because they're going to attempt to maintain a different up vector, they're going to spin on a different axis. Okay, and this is now going to give us a sort of a much more interesting kind of, you'll see here now some of them are rotating up and down and doing all sorts of crazy things. Ones that are almost facing the correct direction already, you'll see very little change with them. But the ones at the back that are having to literally turn around 180 degrees, they are doing some crazy different things. They've all picked their own random direction to try and sort of spin around. Now they still do the full nice 180 degree rotation. They don't flip or pop like it would in a lerp, but they do it on a sort of their own independent axis, instead of if we swapped back to our standard up, then they all rotate around the same axis. okay, which in this case is a little boring. So now that we know what's happening in that, we're just going to go do the same thing, but inside of a pop, okay? So what I'm doing here is I'm sourcing some particles, but you'll see over here, I've actually got a node where I'm removing the points when, like, based on a certain function. And what I'm doing here is I'm modulating, okay? So we take our frame number, modulus to 3, and then we say when it's not equal to 0, then we're going to remove the point. So in other words, we have a point because, let's say, 0. Well, let's say we're on frame 0, right? So 0 modulus to 3 is going to be 0, and so it will keep the point. But then as soon as we move to frame 1, it deletes the point. Frame 2, it deletes the point. But then on frame 3, it's 3 divided by 3 is 1 with no remainder, so that means that we will keep the point. Ultimately, what it is essentially saying is we have a point every 3 frames, okay? So it's yes, no, no, yes, no, no. That's essentially what's happening here, okay? But then I'm also limiting the total frame. So when the frame number is above 15, then we're also deleting it. So basically what's happening here, if I show you, you'll see the center. So on frame 3, I have a center point, okay? I have a point. And you'll see here I'm scattering, but I'm not using these. This was just for our example. Here I'm just keeping my original sphere, and inside I'm going to be emitting from the center of that, okay? So here I emit on frame 3, then 4 no, 5 no, 6 yes, and so on. But then obviously above frame 15, it then deletes it always. So what this results in is sort of a flickering. So this is me creating the sort of firing of these missiles. Okay. So now that we've got that cleared up, on the inside you'll see when I'm sourcing from so all points that are coming in, which it's only a single point because it's a primitive, right? And I've given it some life variance. Okay, so it exists for only 1 second, but it's got a variance of 0.5, so it could be as short as 0.5 and as long as 1.5 because it's variance on either side. And then I've given it an upward velocity, but with a bit of variance as well. Okay, and what that results in, let's just bypass all the rest of this, is going to give us a few points. Okay, so you see there, and it's firing. Okay, so every couple of frames, it's releasing a point. That point has a slightly different trajectory, but the same general kind of up. Okay, there we are. Now what I'm doing with these, okay, let's discuss the drag. So this is really important to know and to understand about a pop drag. It's something kind of underutilized with the pop drag. Drag is often used to just drag down to 0. In other words, drag is trying to say, I want the particles to come to rest. But then obviously there are forces that are making the particles move, and the drag tries to slow them down. Okay, that's a very common use of it. But one cool thing we can do with drag is give it a wind velocity. So give it a direction that we want, well, a direction and a magnitude, right? So an actual velocity that we want it to maintain, okay? Which is what the wind velocity here is actually doing. You'll see it literally says this is the speed which the particles will be dragged to, okay? And in fact, that's actually a misnomer. They say speed, what they mean is velocity. So they mean direction and magnitude. If it was just speed, it would be just a single float value. And that's kind of the trick here, is we need to give it an actual vector, not just a speed. But in this case, we don't want the drag to have a direction, only a magnitude. Because what we want to do is use the drag as a way to essentially create the feeling of thrust in a missile, right? So the missile has its own thruster at the back. So it is, if it's traveling too slow, it will increase because the thruster is pushing it to match that certain speed. But also the thruster is only applying a certain amount of force, and then the sort of air pressure at the front of the missile, the drag, the tangent drag, all of that is trying to slow the missile down. And so if it has a constant force at the back and a constant air pressure at the front, it's eventually going to equalize itself down to a consistent speed. Now, I mean a consistent speed and not a consistent velocity, because the direction can change, but the speed is going to be consistent. And obviously, if it then gets slowed down by something, it will try to increase itself, because the thruster is then going to push more because the air resistance is less at that point. And then if it gets pushed too fast, so maybe some other force applies and pushes it, and it's traveling too fast, then the air, the wind speed, the drag is going to slow it back down. So it's always going to be fighting to maintain a consistent speed. But the trick is to separate the velocity from the speed, right? So we need to feed it an actual velocity. So I've enabled the vex expression here, and I'm feeding into wind velocity. But what I'm doing is I'm normalizing the current velocity. So in other words, I'm not changing the direction at all. I'm going to tell it, keep the current direction. Whatever your direction is, keep it. But normalize that direction and then multiply it specifically by 10. So what I'm saying is the drag has no impact on the direction at all, because it's using the current direction, whatever it happens to be, but the speed must be 10. And so if it's slower than 10, it's going to try speed up. If it's faster than 10, it's going to try slow down, but doesn't alter the direction at all. And this is a kind of a cool use of pop drag. Right. So you'll see it actually gives us that kind of like a missile look, where it sort of has a certain speed, right? I mean, we can even go, if we want, we can sort of slow down or add no upward velocity here, and you'll see that when they fire, they kind of quickly speed up. Well, let's add a slight up. Let's say 0.1, and let's take away all of the variance. Okay, so they're released very slow up. Okay, so they're released, and then they're meant to be moving slow, but you'll see here that they're accelerating until they reach a consistent speed of 10. So you'll see there, you can almost see how it's accelerating itself. And in the same way, if we had to tell it to have like a very high initial velocity, of course it will, fire really quick. But you can see how it slows down to 10 very fast. But that's because we have an air resistance of 1. So we're saying basically very quickly, I want you to maintain that speed. Okay. So let's reset this all. 10, 1, 1, and 1. Right? So now, when our particles die, I want to put them in a group, because then I want to replicate that group. So we've released these initial kind of bursts, these missiles, but when they die, they burst into these kind of cluster of missiles that also have the drag. That's why this drag is applied at the top, because it's then applying to the whole stream. Okay, or we could apply this at the bottom if we wanted, actually. So that we definitely know. Let's move this here just to make this clear. Okay, that this is being applied to the whole system. Okay, so what's going to happen is when they die, that dead group is going to be used as the source for the pop replicate. Okay, so for the reference stream of the pop replicate, we're going to look at the dead group only, and we're going to pop replicate. So we're creating a certain number of points here. I'm saying like 500 points, and I haven't changed the life expectancy as well, so they're going to live for a very long time. But I am giving it quite a lot of variance in the direction that their initial velocity, because I want them to kind of burst outwards and then fix their orientation and head for the target. Okay, so you want them to sort of start off with chaos and then order themselves and sort of lock on to the target. Right. So we've got this variance here when they are replicated, and they obviously only replicate once, because the particles are only dead once. They put themselves in the dead group on the frame that they are dying, they get referenced and seen by the group, and therefore by the pop replicate, they get replicated, but then on the next frame, they're not in a dead group anymore because they just literally don't exist. Okay, so that's how the dead group works. I know it seems a little weird and counterintuitive, but they don't die immediately. They get marked as dead, and then they get removed. Okay. And then in our pop wrangle here, which I'll go through just now, but this is essentially doing everything we discussed in the previous wrangle, okay? But we're just applying it in a particle level. And then we've got a pop collision detect, so we're detecting collision with our sphere, okay? Which I'm converting it, and I'm also adding the floor in as a collider as well in case any particles miss, right? So I've got you'll see on the side here, I've got my sphere and a floor around it to catch any particles that miss. And then when we dive inside, so I'm merging that with my original points because some of them will exist at the same time. You know, in the beginning, when the first one bursts, there are still some of our, so these are the burst particles over here, but these ones haven't burst yet. So they're still getting everything applied to them, and they still get the same pop drag applied to it as well, right? So the pop drag applied to it all, everything bursts and then reorients itself, okay? And then collides with the sphere. Now, the main thing we're talking about here is the orientation fix. Now, it's the exact same thing that was happening in the previous wrangle, okay? So very, very similar, but just remember that inside this wrangle, we need to specify what our second input is, which is second input, so the second context geometry, which means the second input of our DOP. So that's our sphere there, which is a single point. So that's our target, okay? So as soon as we set that up, then that means we can use almost exactly the same code. So we've got our target, we've got our random up, we've got our speed. We're then calculating the current orientation, the target orientation. We're then blending between those two using a blend value. Now I'll explain here, this is where it differs a little bit. And then we are rotating just a standard vector to that new orientation, setting that as the new direction, and then multiplying by the speed so that we maintain our speed. Okay, all exactly the same, except this blend value. The difference here is that I want to blend by age, okay? Now, before we even discuss blending by this age, I'm going to show you something because this is an important distinction. If we set our blend value to be 0.1, okay? Well, in fact, yeah, okay. Yeah, so let me explain it this way. If our blend value is 0.1, what we need to do is remember that this is inside of a DOP, okay? So this is a solver. It's making a change every frame. So we're sort of in a loop, okay? We're just in a frame loop here, which means that the blending becomes a little bit different. On the outside, blending between 0 and 1 is what we tend to do because we've got our current and we've got our target. So we will never reach our target unless we blend all the way to 1. But in this case, because let's say we're facing 90 degrees away from the direction we want to, and we set this to 0.5. What that's going to say is on frame 1, you were facing, let's say, along Y, and we want you to be facing along X. Okay, so you're facing up and we want to face right. So on frame 1, it says, well, slurp, so spherical linear interpolate, right, between facing up or facing right. So now we're going to be facing 45 degrees, okay, in one frame. On the next frame, it's going to now say you were facing 45 degrees, but we want you to be facing right, okay? So go halfway between. And then on the next frame, you go from your current to halfway between. So you see that every single frame, we're getting sort of exponentially closer to our target. Now, we will never 100% reach the target if we keep slurping like this. We have to eventually reach 1 if we wanted to perfectly reach that. But you'll notice how quickly something reorients itself if we have values here that are too high, because that was only a couple of frames. Like at 0.5, it was only like 3 or 4 frames where it was almost exactly 100% facing the right direction. So much so that you might as well call it the right direction. So you'll see here, if I do it now with 0.5, look at that, how very quickly they suddenly go to facing the target. Okay, that is not what we want. Okay, and this is only 0.5. We're not even at 1. I mean, if we had 1 here, this would literally be, it would literally just go straight line for the target. Okay, which is not what we want. Now, see here, if we go to a much lower value, 0.1, what happens here is that you see they start to arc. Okay, but even that was very fast. And the reason it's so fast is, like I'm saying, on one frame it goes 0.1. On the next frame it goes another 0.1. So it's kind of accumulating this rotation. So we need to keep these values very low. If we wanted to, have it quite slow, we would maybe have to go very, very low here. And then it sort of immediately starts reorienting itself, but we kind of have a consistent amount of reorientation every frame. Now that kind of looks good in the beginning, but at the end it also doesn't quite really lock onto the target, and so we end up missing. I mean, I think literally all of them missed there. Okay, like maybe if we go 0.05, we'll get accurate enough so that a few of them hit. Okay, so yeah, there you see a couple of them hit, but most of them hit the ground instead of the actual. In fact, I don't think any of them hit the sphere. So you see what I mean? It's kind of like the missile, you want it to start at first very slowly reorienting itself, but once it finds the target, you then want it to be more aggressively like, yeah, okay, I know where I'm headed and I'm gonna follow it. So keeping in mind that the value we want to head towards is not 1, but actually a very small value, like what we just showed, 0.1 or 0.05 or whatever. So that is our target, like the value that we eventually want to reach, but we want to slowly ease into it through age. So what I've got here is I'm controlling my blend using a fit. I'm taking the age of these particles. I'm saying from a start age that I specify to a target age that I specify. Between those two ages, I want you to blend from 0 blending to a blend value that I'm going to give you. And this is because what I wanted to do is for the first 0.5 seconds, so the first half a second, I want them to just head in their own random direction. They're still busy. Essentially, the computer chip inside the missile is figuring out where the target is. So there's a delay before it even starts reorienting itself. And then, even when it does, I don't want it to suddenly jump up to 0.1, okay, which is my blend amount. When we saw how harsh 0.1 can be, even though it is an arc, it's very tight. We don't want it to suddenly do that. We want to lead into it. So only after 3 seconds of being alive should it eventually be actually blending 0.1 per frame. And so that's essentially what we're saying here. Okay, there's a delay of 0.5, and then eventually you'll be 0.1, which means you'll quite aggressively reorient yourself, but not at first. You'll take a few frames to get there. Okay, so this will now cause it to very slowly arc in the beginning, but once it reaches an age of 3 seconds or more, then it's going to be 100% focused on reaching the target. So let's say it did miss. Maybe we animate our target and it misses. Once it misses, it's gonna be on it. Like, it's gonna turn really, really quickly. Okay, so that's all I'm doing here with this blend value. And like I said, because it's happening per frame, we don't have our target blend actually set all the way to 1, because that would still be way too harsh. Okay, you'll see that now, because of the age, it will at first for 0.5 frames, like 0.5 of a second, it will not do anything. So it just goes in its own direction. and then it starts to change direction. But when it does, man, it really does like go very straight into like a straight line, and that doesn't look very nice. Okay, the beginning is kind of okay, and then suddenly it just looks unnatural. So we want to maintain a 0.1 as a maximum, because even 0.1, it essentially means that within 10 frames it's going to reorient itself almost perfectly, which is very quick. But at least we're slowly blending in to that 0.1. And then, as I said, because we have a random up instead of feeding it a static up, they also seem to kind of spread out. You'll see when they burst, they all kind of do their own thing as they try and figure their way out to reorient themselves. If we gave it here up equals 0, 1, 0, okay, so I'm overriding this up value, then you'll see they still do, because they've got a bit of variance, they are all sort of facing a slightly different direction, but they rotate the same way, okay? They all kind of go, okay, let's spin around the y-axis, which in this case, I mean, I guess it depends. If you want to do like more like precise military kind of homing missile, then maybe you wanted to do that. But I thought it kind of feels a little bit unnatural, and I prefer a nice kind of randomness to this. So they all pick their own kind of spin axis, and they get themselves oriented, and then slowly they manage to hit the target. And of course, we can now, if we reduce the blend amount or increase the end age where it eventually blends in, then you'll see that they are a bit slower on the uptake. So although they do hit the sphere, some of them miss. Okay, so we've got some of them hitting the sphere and some of them missing and peppering the ground around it. Okay, which is cool. I mean, maybe that's what you're after. Okay, so you could have it sort of explode and try and sort of chase down the target. But well, let's bring that in. So you'll see here as these missiles come in, you know, some of them hit. I mean, some of them are actually hitting the back, because that's how slow they are. They actually arc nice and in a big circle, because they're slowly trying to maintain and face the circle, so face the target. But because of the drag we created here, their thruster is pushing them. Sorry, not that. Yeah, here it is, the drag. The thruster is pushing them forward by more force than they are able to kind of reorient themselves. So it ends up creating these nice arcs, and it hits the circle at the back, which is, you know, it's kind of interesting. So this is how we would use quaternions to achieve an effect that would otherwise need to be maybe animated, or you'd need to create kind of curves and have your particles following a curve, and then that can look very unnatural because there's nothing else being taken into account. Here we could add in like random, you know, we could add a pop force that has maybe some wind or whatever, like a wind direction, and maybe some noise as well. Like let's set that to 1 and that to 1. So there's a bit of noise offsetting these and whatever, and yet they'd still kind of, even though there's some randomness to it, they will try their best to reorient themselves and fight against the forces that we're applying to it, right? Now, you wouldn't be able to do that with curves unless you really coded it very well. So very simple wrangle, you know, a couple of lines of code, and we're able to achieve something really nice and naturalistic. And that's all because of the power of quaternions. Okay, so I hope this helped show how you can use this in practice.